All right, let's jump right into this explainer. Welcome, everyone. Today we're going to explore what is honestly one of the most fundamental yet incredibly satisfying aspects of science, untangling the messy, jumbled-up materials of our physical world. I mean, think about it. Nature rarely gives us perfectly pure substances. Pretty much everything out there is mixed up in some way. So our job today is to learn how to play detective. We're going to use the unique physical traits of materials to separate them back out.
So here's the big question we're tackling today. If you've got a chaotic jumble of different ingredients, how exactly do scientists go about unmixing them? If you bake a cake, you can't exactly pull the raw eggs and flour back out once it's out of the oven. But in chemistry, a whole lot of combinations aren't permanent like that. Sometimes things are just sitting right next to each other, sharing space, without actually changing their core identities at all. And that is exactly the kind of puzzle we're going to solve.
Actually, scratch that baking analogy for a second. These colorful beads perfectly represent what we're talking about. Just imagine each color is a completely different substance. They're all tossed together in one big pile. But if you look closely, the red beads haven't somehow merged with the blue beads to create purple beads. They are just sharing the same space. They stay completely independent. And this is exactly how scientists visualize a chemical mixture down at the particle level.
And that brings us to the formal definition, the real core of this whole concept. A mixture is a combination of different substances that are not bonded together chemically. Because they aren't chemically combined, each individual substance keeps its own unique physical properties. It doesn't lose its identity just because it's hanging out in a crowd of other materials. And that, my friends, is our golden ticket. Those leftover physical properties, they become the exact clues we need to solve the puzzle and separate everything back out.
Okay, Section 1, Unmixing the Mix. Let's start with a really straightforward puzzle to see how these physical clues actually work in practice.
Let's say you're looking at a totally messy bowl filled with dark iron filings and bright yellow sulfur powder. They're just completely stirred up together. Now, you could try picking the tiny iron flakes out with tweezers, but, well, that would take you years. Instead, we use physical properties. Our clue here is magnetism. Iron is magnetic. Sulfur is completely unaffected by magnets. So you literally just wave a magnet over the bowl, and boom, the property of magnetism pulls the iron right out, leaving the pure sulfur behind. Puzzle solved in a matter of seconds.
Moving right along, Section 2, Evaporation and Condensation.
So, liquids present a slightly trickier puzzle because solid substances can completely dissolve and just seemingly disappear right into them. Imagine you have a beautiful blue solution of copper sulfate completely dissolved in water. The solid has vanished. How on earth do we get it back? Well, our physical clue here is that water can evaporate into a gas at room temperature, while copper sulfate definitely cannot. By simply placing the mixture in an evaporating dish and just leaving it sitting in a warm room for a few days, the water slowly changes state and escapes into the air. And what's left? The solid blue copper sulfate crystals safely behind in the dish.
But hang on a second. What if we actually want to keep the water too? In that last example, the water just floated away into the room, lost forever. Let's look at a mixture of food dye and water. The crucial point here is that if we want to save both the pure water and the food dye, we have to exploit their drastically different boiling points in a really controlled environment. Water boils at a neat 100 degrees Celsius, but the dye has a much higher boiling point.
This is where we bring in one of my favorite pieces of lab gear, the condenser. We heat the mixture in a flask. Because of those different boiling points we just talked about, the water turns to a gas, steam, and rises up, leaving the dye sitting there in the flask. But instead of letting that steam escape into the room, it travels down a special tube. See how cold water is circulating all around the outside of this tube? That cold jacket cools the steam right back down, instantly condensing it into pure, separate liquid water that drips out into a brand new beaker. Just like that, we've successfully captured both parts of the mixture.
All right, Section 3, the sandy salt puzzle.
We're upping the stakes now from 2 ingredients to a 3-part problem. Imagine you're at the beach and you scoop up a bucket of ocean water from the muddy shore. You've now got a really messy mix of sand, salt, and water. Think like a scientist for a second here. What physical clues do sand and salt have that make them behave completely differently when they're sitting in water? That specific difference is exactly what we're going to use to pull this entire mixture apart, step by step.
The absolute key clue here is solubility. Salt dissolves in water, sand absolutely does not. Because the sand stays as relatively large solid particles, a simple piece of filter paper is literally all we need for step 1. We place the paper in a funnel and pour that muddy mixture in very slowly.
The paper acts like a microscopic bouncer at a club. It traps the large sand particles, while the tiny water particles, which are carrying the dissolved salt right along with them, slip right through those tiny pores and drip out the bottom.
You can see how this setup actually looks in practice. The filter funnel acts as our first puzzle-solving tool. As the sandy, salty water is poured carefully, and you have to be careful. You never want it to go over the edge of the filter paper because it tears so easily when wet. The sand gets left behind in the funnel. And down below, in the conical flask, we're collecting a perfectly clear liquid. But keep in mind, that liquid isn't pure water yet. It's still hiding all that dissolved salt. So, phase 2. Once we have just the clear, salty water in our flask, we fall right back on our previous clue, boiling point. We pour that clear liquid into an evaporating basin, put it over a Bunsen burner on a tripod, and heat it gently to boil off the water. Now, safety is absolutely paramount here, guys. You must wear safety glasses, and the very second the liquid gets low and starts to spit hot salt, you take it off the heat immediately. You just let the residual heat finish the job until it's completely dry, leaving you with perfectly clean salt crystals.
And that brings us to our final challenge, Section 4, separating two solids. Let's see how you'd plan an entire separation experiment entirely from scratch without the water already being there to help you out. Let's say I hand you a beaker filled with fine black carbon dust that is just thoroughly mixed with white table salt. How would you separate them? Now, neither of them is magnetic, so we can't use our cool iron trick. They're both just sitting there as dry solids. To solve this one, you have to get a little clever and introduce a new element to exploit their hidden differences.
By combining the clues of solubility and boiling points, we can actually build a complete multi-step plan to isolate both solids safely. First, we just manufacture our own liquid mixture by adding water. The salt dissolves, but the carbon dust doesn't, and suddenly you've transformed this into the exact same problem as our sand and salt puzzle. Step 2, you filter out the undissolved carbon using the filter paper. Step 3, you take the salty water that dripped through and evaporate it in a basin to get your salt back. And step 4, literally always the most important rule in the lab, keep those safety glasses on while heating. It's all about looking closely at the unique physical properties of materials, whether it's magnetism, solubility, boiling points, or honestly something else entirely. Understanding these traits turns any messy mixture into a completely solvable puzzle. Science literally gives us the tools to see the individual parts hiding within the whole. So the next time you look at a messy combination of things, don't just see a jumble, look for the clues. What will you unmix next? Thanks so much for joining me on this explainer, and keep thinking like a scientist.